So today I want to cover a fairly interesting integral. The integrand, x e to the power of the square root of x squared plus 1, has the square root of x squared plus 1 term in the exponent, which could use some simplifying with a substitution. So I would like to substitute u equals x squared plus 1, but since the derivative of x squared plus 1 is 2x, we would need to have a factor of 2x in the numerator to do the substitution. So here's what I'm going to do. Since we already have an x in the integrand, and we need a factor of 2x, why don't we just take out a constant of 1/2 outside of the integral and rewrite this as 1/2 times the integral of 2x e to the power of the square root of x squared plus 1 dx. Since we have the factor of 2x in the integrand, we can now do the substitution u equals x squared plus 1, which means du equals 2x dx, and if we substitute this into the integral, the expression becomes 1/2 times the integral of e to the square root of u du, since the square root of x squared plus 1 in the exponent becomes the square root of u, and the 2x dx is replaced by the du. To deal with the square root of u in the exponent, I'm just going to do another substitution and let v equal the square root of u, which means dv equals 1 over 2 square root of u du. If we multiply both sides of this equation, we get du equals 2 square root of u dv, and since v equals the square root of u, 2 square root of u dv is just equal to 2v dv. So du equals 2v dv. If we substitute this into the integral, we end up with 1/2 times the integral of e to the v times 2v dv. Since the square root of u in the exponent is replaced by v, since we let v equal the square root of u, and du is replaced by 2v dv, since we just worked out that du equals 2v dv. We can also bring out the constant of 2 in the integrand outside of the integral, and the 2 would cancel out with the constant multiple of 1/2 outside of the integral. So this all just simplifies to the integral of v times e to the v dv, and what I've done is I changed the order of the product in the integrand. By this point, we have significantly simplified the integrand after doing 2 substitutions, and to deal with this integral in terms of v, we can use integration by parts. I'm going to use a and b as the variables for the integration by parts instead of u and v, just because I already used u and v. So for the integration by parts, I'm going to let a equal v, which is the expression we need to differentiate, and db equal e to the v dv, which is the expression we need to integrate. This means dA equals dv and b equals e to the v. If we apply the integration by parts formula, the integral of v times e to the v dv is equal to ab, which is v times e to the v minus the integral of b dA, which is minus the integral of e to the v dv. So the integral of e to the v is just a standard integral, and it's just equal to e to the v, so the entire expression is just v e to the v minus e to the v, and we also have to add the constant of integration c. So I'm just going to remind you that we originally substituted u equals x squared plus 1, and v equals the square root of u. So let's substitute the square root of u back into the expression for the v. Since v equals the square root of u, the expression we have right now is just equal to the square root of u times e to the power of the square root of u minus e to the power of the square root of u plus c. So I'm just substituting the square root of u whenever there is a v in the expression. If we substitute x squared plus 1 back into the expression for u, the expression becomes the square root of x squared plus 1 times e to the power of the square root of x squared plus 1 minus e to the power of the square root of x squared plus 1 plus c. So the integral of x e to the power of the square root of x squared plus 1 is the square root of x squared plus 1 times e to the power of the square root of x squared plus 1 minus e to the power of the square root of x squared plus 1 plus c.